Hi, welcome to a very important lecture in linear algebra. For the entire semester, we promised that we are going to explain the triple spring double mass system, and today we are going to do that. Let's go ahead and take a look at this demo one more time. So this was something we looked at the beginning of a semester. We said we have a system, two masses, three springs, and then when we set this thing in motion, we see a particular movement. The question is how to explain that. This is considerably more important than a single spring. It actually requires linear algebra, and that was a motivation for our course. So let's go ahead and start our lecture today. So we are going to explain the triple spring system. To do that, I'm going to go through several review materials, and hopefully we can put all of this thing back together. Our lecture is going to be a bit more dense than the usual because we have to review many stuff, and I hope that you enjoy it. You are not going to have homework related to this directly, but indirectly perhaps. So first of all, let's start with some basic review of items from calculus. So review, uh, we are going to start from calculus. Okay, let's go back to, well, we're talking about oscillations. So of course sine and cosine are the building blocks of oscillatory movements. Let's go ahead and remind ourselves how to differentiate these things. So if I have a function of time, so x of t is a function of time. Let's take 5 cosine of 2t and say plus 7 sine of 2t. An example of a oscillatory function. Now how do we differentiate this thing? What is x prime of t? You remember derivative of cosine is minus sine and derivative of sine is cosine. So let's just remind ourselves cosine is minus sine and the derivative of the sine is just cosine. In addition to that, we have the chain rule. When you take a derivative of cosine of 2t, the interior function is 2 times t. When you take a derivative of that, a factor of 2 comes out. Let me write it explicitly. So 5 times 2, cosine becomes minus sine, and then 2t. Same thing happens here. We are going to have 7 times 2, and now cosine of 2t. We need acceleration, so second derivative. Take another derivative, derivative of sine, again is cosine, and another factor of 2 comes out, so minus 5 times 2 times 2 times cosine of 2t, and this one, derivative of cosine, is minus sine, so minus 7 times 2, another 2 comes out, and then sine of 2t. If you look at this thing closely, we see x double prime of t. I can factor a minus 4 out of this. So 2 times 2 is 4. And then inside I'll have 5 cosine of 2t plus 7 sine of 2t. Well, this is exactly that. So what we see is an interesting property, that second derivative is a multiple of the original function, minus 4, and then this is just x of t. So let's do a quick practice here. Let me see if you can do this one for me. So I change things slightly. Suppose I have x of t, and instead of 5 and 7 I could have used any numbers, so I'm not going to be particular with those things that are not significant right now. Let me write cosine of, this time let me write 3t, and instead of 7 I write b sine of 3t. Okay, You go ahead and find for me what x double prime is. X double prime. So take a minute to find out the x double prime and find out a relationship similar to this one for me. What do you find? Of course, so okay, so let's prompt everybody to actually do this. X double prime, you find it yourself. You see that you're going to get minus 9 times x of t. Of course, a 3 comes out, second time another 3 comes out, a 3 times 3 becomes a 9, and just like in this case, 4 is 2 squared and 9 is 3 squared, and so on. Okay, let's do the reverse of this problem. Suppose I had x double prime of t is equal to minus 25 x of t. Okay, so this is something that you see in your differential equation class. Differential equation, you might have taken it or not. The question in differential equation, the topic is that we have a relationship between derivatives of a function and that function, and we want to go ahead and find the function itself. So the game in differential equation is the opposite of the calculus game. In calculus you go this way, and in differential equation you go in reverse, and of course going in reverse is always a lot harder than going straight forward. So xt, well, based on the practice that we had, is easy to guess for us based on the pattern that we have, that we have to take square root of this. We cannot determine what's a or b yet, but we can tell that instead of 3 I need to have a 5, so I'll have a cosine of 5t and b sine of 5t. Okay, so far so good. Now let's go ahead and try to settle the issue with respect to who is this a and b. Let's settle that before we go any further. So well, to figure out what each of these things are, we have to kind of remove everything else from our site so that we isolate that particular item. So how can I isolate a and get rid of everything else? Easy way. Instead of time, general time t, use time t equal to 0. So x of 0. If I put 0 on the right hand side, I remember from my trigonometry that cosine of 0 is 1 and sine of 0 is just 0. So this boils down to just a. So a is x of 0. Well, if you understand x of t as a location at time t, this is going to be location at time 0. Well, what you call location at time 0, you use better wording, you call the initial position. So initial position, as in where does something start at, that's x0. How about extracting b? Well, the easy way to get to b is to get the derivative first. I take a derivative, so it becomes in this case minus 5a sine of 5t and then 5b cosine of 5t. Now I see that x prime of 0, now the sign goes away and I'm surviving with just 5b. So b is going to be x prime of 0 divided by 5. Who's x prime 0? Well, that's going to be in the manner that we had here. X prime 0 is going to be initial velocity. So this is going to be 1/5 of initial velocity. So putting everything back together, my x of t, instead of a, I have to write x0, my initial position, times cosine of 5t, and then instead of b, I have to write x prime of 0 divided by 5 times sine of 5t. Okay, now let's hope that we can put all of this thing in a general setting. Suppose I have an equation that says x double prime of t. Now instead of all these examples that I had 4 and 9 and 25, let's just put some arbitrary number here. That arbitrary number, maybe I call it say alpha. Okay, so we had 4, 9 and 25. Now I'm going to put just alpha, and of course you remember in all of these relationships we have a minus, that's particular to sine and cosine. So what would be the solution of this? So the solution of that would be x of t is equal to, so we said we have to take square root of this thing. So I'm going to write cosine of square root of alpha times t, all of that, times x0. I'm going to write it on the right hand side so that it conforms to what we are going to do with matrices later on. Okay, this 5 was square root of, for example, over there we had 25. We had 25, took a square root and divided by that. Let's write it in the following fashion. So I'm going to take alpha, I have to take square root of it, put it in the denominator, all of it, I write alpha to power of minus a half. And this was sine of radical alpha t, and x prime 0, well, that was my initial velocity. Okay, if you understood this, you are halfway through your differential equation class. X double prime of t is equal to some negative multiple of x of t. The solution of that is this. So what we are understanding is really oscillation of a single spring or a pendulum. So you are going to see in your basic physics or engineering class. Let me show you something. So this is the triple spring double mass. That is one level more complicated than this one. This is a basic spring. You probably have seen it in middle school. I was about to say medical school now. In the middle school, you see this, yes. In home, you play with a variety of toys, probably slinky or something, that they act like this. So there is a spring, a mass is attached to it, and it's oscillating. And well, the explanation of that movement requires what we just did here. So what we have done so far up to here is explanation for a single spring. I'm going to explain that single spring. How does single spring end up being this mathematical formulation? To see that, we need some basic laws of physics or engineering. So that one, to the next review item, we have something called Hooke's law. Hooke's law explains what happens in just that spring we were looking at, or any item that you can kind of stretch and it bounces back to the original position and oscillates. So if I have a spring, just like that spring we were looking at, when I attach a mass to this thing, okay, when you attach a mass, of course it stretches. So we have a stretch. As a result of that stretch, there's going to be a force acting on this mass that's going to try to pull it back. So we have a force, and then we have a stretch. Hooke's law is very simple. Hooke's law says if you want to double the stretch, you have to double the force. Kind of makes sense. If you have something is stretchable, you want to stretch it more, you have to apply more force. Of course, it's an approximation. At some point, anything that's stretchable is going to start to break to pieces and so on. So for a while this object is elastic and bounces back and such, it's true that the force is proportional to how much you want to stretch the object with. But the constant of proportionality depends on how tough this item is. So if you play with this slinky, it's kind of a flimsy piece or something, a little bit of a force, it opens it. But if you ever played with that, the spring on top of your garage door, and you should never do that because it's a very dangerous thing. That thing packs a lot of force, and it's not easy to twist that one. So depending on what kind of object you have, the constant of proportionality is going to be different. So Hooke's law says this force is proportional to the displacement to stretch. The force in opposite direction of this, you pull this thing down, the force on the object is, the force that the spring acts on the object is going to be in the opposite direction. So for that reason, there's going to be negative here. And then there is some constant of proportionality. We just write it as a K. You will spend quite a bit of time in your engineering classes to figure out what the K is and what it is for different material, and a lot of topic related to that. But for now, that is enough for us. So this was the stretch. This was spring hardness constant, and this is of course the force. Let's go just while we have this, might as well play with it. So you see the force is shown by this blue arrow. When you compress this spring, then the force of the spring on the object is to push it down. If the object compresses more, the force is more. If the object is down, then the force is pulling it back up. You notice that force is always opposite of displacement, and it's proportional to how much the spring have been stretched. Okay, how's that? How's this simple idea same as that differential equation? We need one more ingredient, and that second ingredient is perhaps the most famous engineering formula you know, and that's Newton's law. So we can squeeze it here. Newton's law. Newton's law in physics or engineering, perhaps as famous as a Pythagorean formula in mathematics. What does Newton say? Newton says force is equal to, let me see if I can get a chorus out of you guys, m, which is mass, times what? Times a, which is acceleration. So Newton's law says in general, if the total force on an object whose mass is m, constant mass, has to be constant mass, then it's going to have an acceleration which is shown by a, and F is equal to ma. Acceleration, you remember x for us is the position. You take a derivative of this, you get the velocity. So this is something you study in both in math classes, engineering classes, physics classes. X double prime is going to be what then? Derivative with respect to time. We're taking derivative with respect to time. This is going to be acceleration. So whenever you have these things, essentially you have derivatives, and the derivatives are what give rise to differential equation. So pretty much anything you study at the beginning of physics or engineering classes is a sort of a differential equation. Okay, still mystery, where does this come from? Okay, let's go ahead and explain that. So the particular force we are looking at is the Hooke's law, and this is always applicable whatever force you got. So this force, let's suppose all that we are dealing with, not complicating anything, adding any more, no friction, gravity or anything. So F is just minus kx. So I have now I'm going to have minus kx is equal to ma. So now we are getting Hooke and Newton. Putting them face to face, that's what we get. Okay, now what? Well, remember from calculus, a is second derivative, so minus kx is equal to m times second derivative. Let's rearrange this thing. I write x double prime is equal to, I divide by m. You see, that is what we had here. If you have second derivative is equal to negative multiple of the original function itself, we know from our practice in calculus how to solve that. So all that we are going to do is to replace this alpha here by something meaningful. Over there mathematically it was just any number, but now we know what's the meaning of that number. The meaning of number is a hardness constant of a spring you got divided by the mass of the item that's dangling from that spring. So again, going to this, if you want to play with it, so you go to FET Colorado edu, and they'll have a huge list of demos you can play with. This is the one for springs and masses. You pick that out, and then you can control the spring constant we were talking about here. You can make your spring tough or flimsy or something, and lots of other things you can play with. And then you can measure the period of oscillations and so on and so forth. So it's a kind of a digital demo of this concept. Okay, so what would be our solution in this case? Our solution will be x. So we have that equation. It came out of Hooke's and Newton's law. We can solve it, and as a solution, what do we get? We get a description of how the thing moves. What would that be? I just copy that, except instead of alpha, I'm going to write so cosine. Now instead of alpha, I have radical k over m. I promise you, you're going to see radical k over m over and over again in your physics and engineering classes. Times x0. x0 is initial position. Initial position. Let me again tell you what is initial position. You go here. Okay, let's stop this. You can take this thing. Okay, if you're doing an experiment in the lab, you can hold this thing and stretch it, start it anywhere you want. That is starting position. That's very easy to control. The starting position of the oscillation. The other one is not so easy to arrange in the lab, but mathematically we can always have a thought experiment doing something. So x0 is very easy to control. How far do you stretch this thing before you kick it moving? And then I'll have k over m, the power of minus half. So that's a square root, and then in the denominator I have to put this thing minus a half. Then the sine of the same thing, radical k over m times t. And then, well, if you set something in motion, like here, if you set this thing in motion, you can give it a kick, and that kick is gonna set the initial velocity. You can let it go. Letting it go means you're not kicking it. The initial velocity is 0. But if you kind of take a hammer and just strike this thing so that you give it an initial momentum, then you have that control as well. So, okay, we have a major achievement here. We have the solution of the regular spring. Here is how a regular spring gonna oscillate. Now what? Now for the finale. Now where the fireworks start. Are you all excited? I'm sure you are. Okay, so now we have double mass, triple spring. Well, the is no free lunch. We have to work a little bit hard to get there, and that's what we have been saying all along the semester. uh, you are going to entire linear algebra class for what we are going to say next to make sense. Okay. Okay, now I'm going to break it into two pieces. One is uh, just give the mathematics of it, and then for those of you who have taken your physics classes and ready to do a bit of force diagrams and so on, I explain the detail of that as well. So what happens next is that, well, you got this thing, a mass, and then another spring, and then another mass, and then another spring. And by the way, you could have had even more of these things, but uh, two is enough to illustrate the idea. So we have two masses. Let's call them mass number one and mass number two, and three springs. Let's consider the spring constants of this one: K1, K2, K3. Things are a little bit off kilter here, but there isn't much you can do with that. Now, instead of x that we had there, which was a displacement, we have to keep track of displacement of this mass 1, displacement of mass 2, and sometimes in some problems these endpoints are moving as well. Instead of like in this demo, the endpoints are tied to what seems to be a permanent fixture, but you can imagine somebody holding one end of this thing and maybe oscillating it, and so on and so forth. So we can even think about something more general than that. So displacement of this one, let me call it x1. Displacement of this one, let me call it x2. So from the neutral position where they are stationary and all the forces are balancing, from that position we are going to measure how far to the right or left this one has gone, call that x1. How far to the right or left this one has gone, let's call it x2. If you want to play with this end, let's call it x0. If you want to play with that end, let's call it x3. So in simple case, these endpoints are just held fixed like the demo we had. Only x1 and x2 are changing. So instead of a simple x, I have x1 and x2. Now comes the kicker. What do you think instead of k over m I'm going to have? Well, I'm going to have a kind of an alphabet soup of everybody you see here: k1, k2, k3, m1, m2. Not to distract your attention from that, let me go ahead and just use some generic letter to indicate all these entries are going to interact with each other. We are going to explain that later on, and we are going to have some matrix. So instead of k over m, we are going to have some matrix. Matrix would like the letter m for matrix, so it's not a mass or anything. It's a massive thing of all of these guys combined, compressed into that. I'm going to explain that later on. So this equation, instead of x double prime, becomes derivative of a vector is equal to minus certain matrix times that vector. Okay, so put your curiosity about m aside. I'll come back and explain that. So what's going to happen is that when you have a system, instead of these single items, you are going to have vectors. Instead of this single multiple, you are going to have a matrix that's going to represent how all of these guys are going to play with each other. So let me see if you can let your imagination run wild and see how do we write the solution for this. So what we want to do is to write what is x1 at time t, x2 at time t. Just like we solved that, we want to solve this. And that is what takes a linear algebra class, because what we want to write is really, it looks exactly like this. It's cosine of matrix M times T times the initial position. Now we have two initial positions. Where was the item number 1? Where was item number 2? And then we are going to have that matrix raised to the power of minus a half. How do you raise a matrix to the power of minus a half? That's why you take linear algebra class. Sine of, excuse me, I made a mistake here. Let me correct myself. Write this thing again. Actually more complicated than what I was saying. Square root of M times T. We were taking square root here. I forgot to put the square root. Square root of M times T times, what do you think I'm going to put here in this vector? Of course, it's going to be initial velocities. x1 prime 0, x2 prime 0. So you need to know where is the first mass and what is its velocity. Where is the second mass and what's the startup velocity. Then you need to take square root of your matrix. That's a challenge. How do you take square root of a matrix? Then you have to take a cosine of that times t. So we were saying as our goal for the entire semester is that we want to duplicate everything we have learned from elementary school to calculus and do it for matrices. You see why we need to do that? Because I need to be able to take square root of a matrix. So that's a challenge. Then I need to be able to take the cosine of that matrix. So maybe you took a trig class in high school and they told you what's cosine of 30 degrees. This is way beyond what's just cosine of 30 degrees. We spend the whole class to come here. Okay, so this is the solution. This is time for celebrating because we have achieved a major milestone. This is how this thing moves. You have to track these two. You have to put all the numbers into that formula, and then you are all set. Now, note for the finale. What is M? That's easy to write. We have to just write several force laws here. So remember, let's go ahead and focus on this mass number 1. Suppose I want to write the force on the mass number 1. So here, what we are answering is, well, I need to know what is that M to do all of this thing. The mass number 1. Well, there are some forces on the right of it that's pulling or pushing on this side, and there's also forces on the left of it, and that could be pulling and pushing, and that's what makes all the complication, everybody interacting. So we are going to look at this spring. If it is stretched, then it's going to contribute to a force on this thing that's going to pull it to the right. How much is that contribution? Well, I am going to go and check how much is this middle spring stretched. It's stretched by x2 minus x1. Is that right? x2 minus x1. So for example, if this goes to the right 1 inch and this one goes to the right 1 inch, well, the middle spring is not stretched at all. And there's no force corresponding to that to be doing anything. So this will be 0 in that case. If x2 is say 5 inches and x1 is 4 inches, the difference between these two is going to be 1 inch. You can say the middle spring is stretched by 1 inch. Well, whatever this thing is, we have to multiply by the hardness constant of that spring to see how much force is pulling to the right. In case this was negative, it would be indicating a force pushing to the left. Then we have to do the same thing on the left. On the left, this is at x0, this is at x1, so the spring on the left is stretched by x1 minus x0. The hardness constant of it is K1, and that force, if it is positive, then it is going to be a force that is going to push this thing, so I have to subtract that force from this one. Well, I go ahead, do the same thing for F2. Let me see if I can pause this thing, and then you go ahead and write what the F2 is going to be. F2 has a force on the right, which is coming from this K3 times X3 minus X2. And then the force on the left is K2 times X2 minus X1. So if X2 minus X1 is a positive quantity, means this is stretched, and that's going to pull this object to the left. That's why you have to subtract. Now let me rearrange this thing. So I'm going to write this thing with X1 written first, minus K1 plus K2 times X1 plus K2 X2, and then K1 X0, I put it at the end for a reason you're going to see shortly. For here, I'm going to put X1 first, so it's going to, you see, I have K2 X1, and then X2, I have 2 K2 and K3 X2, and finally I have K3 X3. Now these two are your control mechanisms from the end of the system. Typically these are under your control. Or in the demo that we had, we are holding the two ends fixed. So there is no, in the demo that we have, there is no displacement x0 and x3. So in the demo these two are 0. For simplicity we are going to drop them. Next we are going to come and say F1 by Newton's law is m1 x1 double prime. F2 by Newton's law is m2 x2 double prime. So I'm going to go ahead now, divide by m1, and also this items at the end. So I'm going to have sorry, why does this thing move? X1 double prime becomes minus K1 plus K2 over m1 x1 plus K2 over m1 x2, and that we said for simplicity we are setting this thing equal to 0. We have enough complications. So x double prime 2 starts with K2 over, now this is m2 minus K2 plus K3 over m2, and then that's also x2. If you want to pack it, x1 x2 double prime. Let's factor a minus out so that it looks like the formulas we had previously. K1 plus K2 over m1, so this becomes minus K2 over m1, and this becomes minus K2 over m2, and this becomes plus, so there's commas here, plus K2 plus K3 over m2, then all of this times x1 x2. So when we are saying here is a vector of positions, stretches, is equal to negative of some matrix. Here is my matrix. You are wondering what's my matrix, why did I postpone it? Now you see it's not a trivial thing. There was a bit of work involved. There is some sort of matrix here. When you go to your engineering class, they are going to give this thing a name, and you are going to deal with it much more detail than we are doing here. So there is this one. Okay, what are we supposed to do? We are supposed to calculate cosine of radical mt. How do we do that? Well, that is what we achieved last time. So if you have a matrix, certain properties, then you can write it as A certain matrix made out of its eigenvectors times a matrix of its eigenvalues times the inverse of the eigenvector matrix. Okay, so that was the last lecture. We had the diagonalization. So what does it look like? It looks like M, V, this is going to be lambda 1, lambda 2, and then V inverse. These are your eigenvectors. This is the inverse of that eigenvector matrix. These are your eigenvalues. Now suppose you want to just write M, suppose you want to write square root of M. What did we say last time? You just do that to this. Radical lambda 1, radical lambda 2, and that's it. After you spend so much energy to get that, this step is easy. What if I want to have cosine of radical mt? What do I do there? We just do that. Whatever you want to do, you do it to your eigenvalue. So it's going to be cosine of radical lambda 1 t, and then cosine of radical lambda 2t. As simple as that. Well, as simple, provided that you came along for the ride for the whole semester. How about this other component? We have m inverse sine of radical mt. What is that? So m inverse sine of radical mt is going to be v. So this is going to be 1 over radical lambda 1 sine of radical lambda 1t, 0, 0, 1 over radical lambda 2 sine of radical lambda 2t, and then v inverse. So the meaning of these pieces, the two critical pieces are these. Where do they come from? They come, how do we calculate it? From the diagonalization formula we had last lecture. Okay, so now we packed quite a bit of stuff in this lecture. It was one level higher than everything else we had done before, but sometimes students ask, well, why are we doing what we are doing? I explained one reason why we did that. There are thousands of applications of linear algebra. Just about any engineering situation that you quantify, you have numbers down and then you want to analyze it, it boils down to linear algebra at some stage of it. Some of it a lot more complicated than some others, but the thing is always there. We said whenever you have a system, if you have interacting component, we emphasize that here's a system, meaning I have this ball and this ball, this moves, that moves, they influence each other. When you have the influence of several components, here is officially here. These are items influencing each other. That influence comes in a matrix. It's very standard in physical phenomena that you see these ingredients that are always neighboring pieces. The neighboring pieces come into elements of your matrix, and that matrix is going to set the tone for how the system is going to move, and the most crucial part of that matrix is going to be those eigenvalues. Okay, I hope I contributed to your understanding of nature, physics, and mathematics. We are going to go back to our regularly scheduled program, which means doing more algebra. Yeah, I notice I have something missing here, sorry. There's X one is missing here. Okay, so we are going to go to more algebra. What does it mean, more algebra? More algebra means, since you are interested in this so much, more algebra means bigger system, which means what? Which means you have more pieces. Mhm. Yeah, so much fun with that. You can have fun with this one. So if you have three pieces that are freely moving around, kind of freely moving around, then your system is going to be 3 by 3. 3 by 3 is going to be a challenge for us on all fronts. All sorts of things could happen. The minimum of that is that we have to solve a cubic equation. In high school, you typically stop at quadratics, but you do a bit of a practice with cubics as well. So we are going to look at problems where the cubic equation is kind of friendly, and we are not going to suffer too much in solving it. So first stage, when you set the determinant equal to 0, you are going to have a cubic characteristic equation. Then next stage, our matrices are going to, well, 3 by 3 eigenvalues and eigenvectors. Going to take longer time to find, and all sorts of fun that we are going to have with that. So that's going to come up in the future lectures. Until then, good luck and God bless.